Hello everyone. My name is Nagai Daphne, and I'm going to take you through machine learning. And basically, by the end of this video, you should know what is machine learning, why do we even do it in the first place, how is it even able to make predictions, and the models it uses. So we're going to be able to learn all this from this video. So machine learning is a branch in AI that's going to enable computers to learn from data, and it's going to focus on patterns and predictions without explicitly programming it. And the reason why we are doing machine learning in the first place is because, for example, there are actions or rules which require a lot of effort. And machine learning would make life easy if we are able to for machines and computers to be able to learn and predict from this data instead of manually combining these programming these rules in. For example, weather forecasting. Weather forecasting, it can be able to see, okay, what are the predictions, what weather should we expect in January, based on the data, based on what it has been able to learn from the different predictions and the patterns that happen. Now, like for example, we know every November it's going to rain. We are assured of grasshoppers. So it's able to learn from it's going to be able to learn from that data, and that data is used to make predictions. Now, the key concepts you're going to learn is the process of extracting the knowledge from this data, the models and the relationships between the data, then the output of the models and how it's also being able to classify, okay, this is a span or not, maybe this is a continuous data set. So we're going to be able to learn all that. Now, the types of, what are the different types of machine learning? We have two different types of machine learning. We have supervised and unsupervised. Now, supervised learning, we are using labeled data for training. And this is, for example, you're going to be able to give now like predicting house prices. You're going to be like, okay, what's the square meter, maybe in the number of rooms, the location, like you're giving it a labeled data set. And then you can do this through classification. Maybe you're predicting the different types of data. Maybe is it a sperm or not? Is it a cat or dog? Then regression is for continuous values now, like the example I've given on house prices and temperature. Unsupervised learning, here you're using unlabeled data sets to identify patterns. So here you can maybe use customer segmentation, and you're grouping them similarly. Like you're like, okay, my customers best maybe they start giving me I have the highest sales at the end of the month. You're able to cluster. Or maybe there are those customers who are continuing clients, they don't have to do it every end of month. Then anomaly detection is able to detect what are the different anomalies that happen in data and the unusual occurrences that are going to happen. So a model is a phenomenon that's used to make predictions so a computer can understand. We have deterministic models where there is no randomness, not like when you're calculating a loan. I know if I give you 10,000 and the interest rate maybe is 10%, I expect my 11,000 when you give me back my money. So that's it's not random, it's very direct, and there's an exact relationship. Then maybe the equation y is equal to mx plus c, it's a linear what? It's a linear relationship. Then we have probabilistic models that are going to include a sector of randomness, maybe like weather forecasting. It's going to create, maybe we're going to include, we're going to account for uncertainty. So we're going to combine the deterministic component and a random error. Then we have different examples of probabilistic models. We have regression models that are going to explore the relationship between this dependent variable and the independent variable that's going to influence it. Now, like maybe how are we going to predict the sales based on the advertising budget? Then the correlation is going to measure the strength between this relationship. Maybe what's the correlation of someone smoking and getting lung cancer? So we also have other models like time series and classification. So here in regression modeling, we have we have the steps you can take. So let me give an example. Based on these 4 steps, I'm going to use the example of house prices. So here you're going to define your deterministic models. Now here you're going to determine, now like in Tinder, someone is maybe looking for rent houses and you're like, okay, what's the room size and how many bedrooms does it have? Those are your deterministic components. Then you're also going to account for the random errors and you'll be like, okay, a room might be the same size and in the same location, but cost differently. Like maybe they're in the same location, but the one is 400,000, this is 200,000. Then you're going to fit the model to data and evaluate its performance, and you see, okay, how is it performing? Is it correlating? Then you're going to use the model to come up with predictions and estimations, and you'll be like, okay, for houses maybe in Tinder, the model is able to predict that this is the price you should ideally pay for a room. So now we have linear regression. Linear regression, assumes that the relationship between the x, which is our dependent, and then y is linear. So it's going to, it predicts that it's in a straight line. So here it assumes that the assumptions, it assumes that it's in a straight line, and then it assumes that y is maybe independent of x, meaning this maybe y doesn't like 0 doesn't maybe can does not directly influence x, something like that. Then the pros and cons we are already seeing. It's simple to implement. As you can see, it's very linear and straightforward. As you can see, our data is very linear. That like you can already see the relationship between x and y. But then it's also effective to compute it. Then it can interpret the relationship. It can easily interpret the relationships between these models. The limitations, though, it is assuming that this is a linear relationship, which can be complex for non-linear patterns. You're going to see non-linear patterns that may not be as straightforward as this. Then it's also sensitive to outliers, which can significantly affect the model. Then it also requires a careful feature for assumption. So the second one we have is parametric and non-parametric models. So a parametric model is one in which the model you know exactly which model to fit in. Now, like we've seen, we can directly fit linear regression with this. Then examples of are linear regression, but then there is a type of model whereby the model structure is determined by the what? By the model itself. Now, like maybe we are going to see maybe you're making decisions. The model structure is going to be determined by the data you're getting. It's not as straightforward as that. So there is an important concept I felt I didn't want to miss. It's an iris dataset. This is the most popular and widely used dataset in machine learning. It's very simple. So the reason why we are doing this, you want to classify your flowers in 3 parts. But then now the features you're going to use, maybe you're seeing the features. So these are 3 different flowers we have. So you're like, okay, how do I classify my features? So here you're going to use the different attributes. Maybe the sepal width, where you're saying, okay, what's the width between maybe this and this, and then what's the width and what's the length of this and this. So through that you're able to know the categorize and classify this. Then you're able to know the petal length. Okay, this petal length is a bit longer than this is wider than that, so you can be able to use this iris to classify your data. So here we learned in non-parametric models that the model structure is determined by the data itself. So here we have the KNN algorithm. The KNN algorithm is simple and it's commonly used in classification and regression tasks that we saw in supervised learning. So here it's going to use the principle of proximity. Let me show you an example. So here, imagine you have a data set of a cat and dog images, and you're given the image of an unknown creature, this unknown feature. So you're going to compare the features based on the data that you have, and you say what's the fur length, the ear shape, And here you're going to get the closest image based on the similarity of the data that you have. And because of that, you're able to assign your input value what you predict it will be. So here you assign the new image to the category, a cat or dog, based on the majority of the k-nearest, like majority among the k-neighbors. So here, this is can be used in text mining, agriculture, financing, and Kaggle competitions. As you can see, you calculate the distance between the training points, and then you get the K points, the K nearest points, and then you assign it to the majority of the class, like where it is majority, like majority of the class, and you're able to assign it to that feature. So you can say it's very simple to implement, but it can be slower. Imagine you have very many data sets. It can be slower. It works well when you're classifying your data. Then decision trees. Decision trees are basically, it's a learning algorithm that is used to classify and regression tasks. Every time we see classification and regression, we remember our types of machine learning. So here, and it has different features. We have the nodes. These are the nodes. And the nodes are going to represent the different attributes that we have. Then the branches are going to represent the different decisions one has to make. Then the leaf nodes represent the outcomes. Now, this concept can be simply explained in an example that I was able to give. Now, imagine we have a data set and of students, and you would want to know what are their study hours and previous, and want to predict if they will pass or fail. So a decision tree would be the best thing to use here. So you're going to split the tree based on the study hours and the previous grades. So let me show you how this would work. So you split the data first here in the decision node, this root node, the starting point, the topmost node, and you be like, okay, what are the study hours of this student? You be like, does this student maybe study for more than 5 hours a day? If no, then the leaf note, we've already made our decision that it is the person has done what? Has failed. If they do, we make another decision basing on, now here we're using previous grades, and we say basing on their previous grades, do they get a B or a A? If they get a D, we may say they're most likely to fail. And if they get an A, maybe they are most likely to pass. So basically, that's how we use decision trees. So the left nodes represent the left nodes are going to represent the outcomes and predictions. Then we have the different nodes and the branches. So that's how you would use decision trees. So that's basically about decision trees. So we have something called ensemble learning. Ensemble learning is a technique where you have multiple nodes, usually called the weak learners, are combined to create a stronger and accurate model. So here you commonly use it whereby the strengths of one model are going to compensate the weaknesses of others. And it's commonly used for better accuracy, and whereby there is no single module that consistently delivers higher accuracy. So you can use maybe fraud detection, because here you don't have like a single model that's going to deliver high accuracy. So you're going to combine them to come up with a stronger, accurate model. So here we come up with something called bagging. Before bagging is they called it bootstrap aggregating. And this reduces the variance by averaging. So it's going to reduce the variance by averaging predictions from multiple models. How it's going to work, the steps you're going to use, you're going to use bootstrap sampling, and it's going to create multiple data sets by sampling with replacement. That's what data sampling is. It's when you create like multiple data sets by sampling with replacement. Then you're going to also do model training, where it's you're training a separate model on each data set. Then after that, you're going to combine these outputs to get an average. So the knockoff is it reduces overfitting, and then it also can be less it's can be less of a disadvantage if there are multiple models. Then we have random forests. So this is going to use the decision trees as a base model. It's going to add an extra randomness by selecting these features at random. So here, like we used the other example for maybe random decision making. Here you're going to bootstrap, then it's going to use a technique called bootstrapping, where you have multiple data sets on an original data set. But here you're going to pick each node at random, selected with the best split. This presents it becoming less similar. Now, like maybe use an example of houses. Maybe for houses, you're going to use maybe location, the size, maybe the number of bedrooms, but when it's making its decisions here, it's picking them at random, because here, you remember, we're picking them maybe study hours, it was like in order. But then here you're picking your stuff at random. So here for each node, the random, because here we're preventing it from becoming too similar to each other, like you're picking it at random. You're like, okay, let me pick this at random. So you're trying to see trees are grown until a stopping, like until you reach your maximum samples. But here, the key difference is you're picking your stuff at random. The pros, it's robust to outliers because it's not predictable like it is. It's also good for nonlinear data, like we have seen, for example, of the houses and maybe the max. Then it has a low risk of overfitting, and then it's also efficient for larger data sets. And then it's not suitable for sparse data, and then it also has greedy algorithm limitations. Then by so here we have boosting. Boosting, here the trees are sequential, with each tree focusing on fixing errors made by earlier ones. So here how it's going to do. You're going to misclassify samples and get higher weights. The new trees focus on hard cases. Then the final prediction is going to combine the tree outputs, like maybe average and what. So the benefit, it's very highly accurate and but it can overfit if there are too many trees created. So here it's focusing on fixing errors. So here, when we're comparing them, bagging is more, like you've seen, it's parallel. All trees are grown independently, while boosting is sequential, like you're correcting like errors in the previous one, as you can see. Then bagging reduces variance by averaging multiple models. But this one is going to improve the accuracy by focusing on the mistakes made by previous models, then correcting them. Lastly, we're going to talk about principal component analysis. Principal component analysis, this is a technique that's used to simplify data by reducing the number of variables while keeping the most important information. So the key points here is going to reduce the complexity of data by using fewer variables, keeping the most important information while discarding the less useful one. You can already see a disadvantage of this, that some data might be lost. You may say this data is not useful, and then you delete it. So data that may not be used at the moment might be discarded. So here it works well with variables that are linearly related, like we saw in linear regression. If the data has no linear patterns, this here might miss some key details. So here, the importance of scaling. Features should be scaled, like you're standardizing. Standardizing is when you're making sure your values are discrete. Like if you have maybe 1.2, you're able to round off and create like discrete values. So if one feature ranges from 1 to 1,000 and 0 to 1, a larger feature could dominate unless scaled. So you need to scale your features. So here, an example is image compression. When you're compressing an image, or maybe doing facial biometrics, and you're trying to see image compression, you may reduce the image size while also keeping the important details. Now, like for this video might be very large and my computer may decide to compress it. But then when it's compressing it, it should be able to keep the important details. So that's a very common example of PCA, whereby you're reducing the quality, but you should be able to keep the important details. Then we have machine learning processing, whereby you're simplifying data by feeding it into models using classification. Then facial recognition, it's going to use the key features of the faces, maybe the eyes, the nose, and the mouth, to make recognition easier instead of getting the whole face, because sometimes I might have makeup, what, so it's going to pick out the most important features. Then data visualization. You reduce the data from you reduce data to 2D or 3D for easier plotting. So you're getting out the key features. So the main thing here in principal component analysis is you're simplifying your data and you're keeping the most important information. So after PSA, the new variables are combinations of the original features. These components are hard to interpret directly, but reduce the data dimensions. So basically, that's what I was able to learn from this video. And feel free to share a comment, and I can be able to answer you. Thank you so much for listening and tuning in.